Okay, we're going to continue our learning under module 8, which is under synchronized counter. So what we're going to look into, basically under synchronized counter design, there are several of steps that you need to follow. First step is to describe a general sequence circuit in terms of its basic part, and also input and also output. Second, on develop stage diagram. This one you already look into our previous video, our previous notes, which is under module 8E. And then you need to create next stage tables. So last time you look on the state tables, now you need to create a next stage tables. So there is a difference between state table and next state table. Okay, later on you're going to look into it. And step 4, you need to create a flip-flop transition table. And step 5, you need to use the K-map. So still remember what K-map under your module 5. Although it's not will be used in your final exam, but still you need to apply it under of course in simplifications all along your digital logics. So K-map is very important to derive the logic equation. And lastly, the final step is step 6 on implement counter implementation. So this one under step 4, it is execution stable. Later on you will look into it. So here, first of all, we're going to look into the FF execution tables or flip-flop execution tables. So under here, why is because we already learned on step 1, step 2. Step 3 is basically the state tables, but it is next stage table. So we're going to directly move to this step 4 first. So over here, you were given the JK flip-flop condition for your input. Let's say J and K. You have several conditions. If you have to the power of n, you have 8 minus 1. So to the power of 8, 1, 2, 3, 4, 5, 6, 7, 8. All together 8 possibilities for you to have. But if you can see over here, this one is to the power of 2 because there is 2 input. But later on you're going to check why there is 0 0 2 times, 0 1 2 times, 1 0 2 times, and 1 1 also 2 times. What happened? So it is about creating the next stage tables. So that's why you need that. So normally you're going to have to the power of 2 only 4 possibility, which is 0 0 0 1 1 0 1 1. But now you can see this is the true tables for you to create later on. So you need to have the present stage and also next stage. Over here you can see that the present state is 0 1 0 1 0 1 0 1, and the next stage is the one that you need to create. So over here, if you refer back to your JK flip-flop under 0 0 truth table, it's going to have the output as no change. 0 1, the output will be reset. 1 0, it will be set. This one set reset, you need to know the output is 0, and set is the output is 1, isn't it? Output for your Q. And toggle is like a note or a bar. It's going to be a vice versa. If let's say your output is 0, so it will be toggle. If the previous output is 1, it will be toggle to 0. So next, this one is there is notes that you need to refer for your JK flip-flop to table, of course. And this one, if you can see that you have the outputs of your present stage and also next stage. You can see over here you have 0 0 1 1, and if you compare to this, you have basically 0 0, which is no change, from 0, and then next stage is 0, so no change. Or maybe also you can also have 0 1. So if let's say you 0 1, the output will be 0, right? So similar, you can see the output is 0. So this is one of the example how you can see and link it together. Next, if let's say you can see over here, you have 0 1, which is, you can see it's toggle, which is from 0 to 1 toggle, and also from 0 to 1, which is set, the output will be 1 from your previous compared to your previous state. So this one is similar to your previous state, this one is your current state, or in these notes is used as a present state, and you need to draw your next stage through table. So over here you can see that JK0 and K0 or 1, you can see over here. Like this, then you will get X or green color. And if let's say J1, K0 or 1, you will get X, the blue color. So what is going to happen also? So this is basically what happened for your next state table. You have the present state 0 0, and then 0 1, 1 0, and 1 1. Then the flip-flop stage, you need to know that it is, if 0 0 and then another one is 0 0, you will get 0 for J and X for K, because K can be 0 or K can be don't K over here. It is either it is 0 or 1. So anything, maybe it can be 1 or maybe it can be 0 over here. So you will get the output of your present state and also next state as 0 0. While if you, let's say, you can see over here, you have the 0 1 for your output. There is a two condition also, but you're going to have J as a fix over here, that's why it will be 1, and X for your K, because you can have between 0 or 1. And then you're going to see the output of 1 0 1 0 over here. So 1 0 1 0, if you look over here, this is the input of your JK. So your JK is different, 0 or 1, so it will be as X, but for your K is fixed, that's why it will be 1. And another one is 1 1 1 1 over here. So if you can see over here, 1 1 is 0 0 and 1 0. So fixed term is K, that's why it's 0 over here, and the one that changed is J, which is 0 or 1. 0 or 1. That's why it will be X or don't care. So after you get this net state table, you need to draw the state diagram. So your state diagram, you can see over here, this is your so if you want to draw this state diagram, what you need to refer, you need to go back, refer over here. Okay, if let's say this one is your output 0, so from here you can see that if let's say it is 0 0 for your JK, if let's say your JK is 0 0, you can get either 0 to 0. From 0, let's say present state, normally I use it as a previous, and then this one is current, but it's quite similar. This one is present state. Your next state from here is going to be here, right? So if 0 0 condition, this one, from here to here you will get 0 back. You can get this one, but in this also you can see over here 0 0, you can also move from 1 to 0. So later on you will see that from 1 to 0, this is another one, from 1 to 1, so you will do like this, and the condition is 0 0. This is 0 0. First condition, it is from previous present state is 0 and next state is 0. So this is first condition, and the second condition, it will be this part, which is from 1 to 1. So it will be like this, from 1 present state to the next state, like this. From your present state 0, and then it will be the next state also the output as 0. So the condition is 0 0. Next, let's take a look on the conditions of 0 1. So condition of 0 1, what you're going to see is you have two conditions also, which is 0 0. From previous state 0 and to your next state is 0 also, there is a condition of 0 1. This is your conditions, which is 0 1. And then the next conditions, this one, 0 1. So your next condition is from 1 to 0. So if let's say you can see over here, this is from 1 present state, you will draw like this to go to 0. So this is another scenario. So I need to repeat again as to make you clear. So next is still under 0 1. So over here your condition of 0 1, you have over here and here, which is first is your output for your present state to your next state is from 0 to 0. So if let's say you have the output of 0, so your conditions is 0 1, you have 0 to 0. So it's going to out, let's say it's going to go to your next state, but the output is similar, so that's why you return it back. From this starting this bubble, let's say, and it will go to your next state, but your next state the output is also similar, it is 0. So you have another output, if let's say it's 1. So over here another one is, let's say let's say I give you example, your conditions 0 0 is from next present state is 0 and your next state is 1, so you will be draw like this. So this one is just example. In this scenario, in this case, if you look over here, 0 1, so you have the condition of 0 1. This is your conditions, and this is the output of your stage. You have 0 and 1. So from here you can see from 0 to 0, this is your first condition, like this, from 0 to 0, and then from 1 to 0, 1 to 0. So this is another condition which is 0 0, 0 1, and then this is also 0 1. So this, I hope that you understand. Okay, I repeat again for your 0 0. For your 0 0 condition, you can see your present to next stage is 0 2 0. So it will be also similar like this. So there is another condition which is 0 0. And then it will be 1 to 1. From 1 to 1. I can draw like this. I can also draw like this. There is no rules of clockwise or previous or counterclockwise, as long as your error is from the stage which is 1 to another state also 1, so either one, but you need to also put your condition. So the conditions is over here, it is 0 0. Okay, hope that you understand. So refer to this state diagram because it's much more beautiful. Okay, next is under the blue color. You can see over here your conditions is 1 0. 1 0, it is from 0 to 1. So you will draw from 0 to 1. So your condition is 1 0. And after that you have 1 to 1. From 1 to 1. So from 1 to 1. So this is the condition. And another one is under your condition 1 1. So from what you see over here, the output will be 0 to 1. So it will be like this, 0 to 1. So this is the condition which is 1 1. And also from 1 to 0. So from 1 to 0, this is the condition. So again, so after you draw these two condition, this one is very simple example because you have two states only, which is 0 and 1. But if you have several states, then it will be quite difficult. As long as you know the basic, then you will understand and easily to do many states. And if let's say this is the condition, so you need to check 1 1, it will be fixed as 1, and then 0 1. You can see over here, don't care anything whether it is 0 to 1, so that's why it will be X. If you refer to this next state table, 1x, you can see what will happen, your present to your next state. That's why you get like this. And then over here, 0x, this is your 0x. You can see that it is from 0 to 0. That's why you get like this. We have another one from this part, x1. x1 is here. x1 is here, so you can see the output change from 1 to 0. From 1 to 0. True, right? So lastly, x0. x0 is this one, so the condition is from 1 to 1. So if you don't want to do this part, also can, as long as after that you already understand why you will get these next state tables from this table. So it will be easier if, let's say, you understand the next state table. If 0x conditions for your JK input, if I repeat again, if let's say your condition for your JK, this one is your condition for your JK, this one is your output. It changes the stage from your present stage to next stage. It is 0 0. So you will draw like this without and this one will be 0x. But as long as you understand why you will get 0x over here from this table, then it's also vice versa what I teach previously. And then you have 1x. 1x you move from 0 to 1. Maybe I can give you the clear example I draw over here. So from this table, I will draw like here. Okay, you have the outputs of 0 and 1 only. So let me draw. Okay, this is the output. And now I have the condition of JK. So the condition, this one is condition of JK. And let's say the input is present state from 0 to 0. Then I need to refer to the condition. The condition is 0x. And then next is from 0 to 1. From 0 to 1. The condition is 1x. Next is 1 to 0. The condition is x. 1. And lastly 1 to 1. I can draw like this also. It is x or 0. This is the basic things. Later on you will have much larger. So let's move. If you have questions that you did not understand, please ask me, WhatsApp me, or ask me in class. So let's take a look on the exercise and the D flip-flop and using its state diagram. I think it's quite similar. It's not showing here. Maybe you can check on your module. It is just a simple example of your exercise. From all of that, you can see over here, if you look on your exercise, you have D and T flip-flop for your exercise. Let me check. Okay, it's not there. Supposedly it should be here. I think I deleted it without I realize, but it's okay. I already show you the basic thing over here, so it's very clear on how you're going to create the next stage and also your state diagram. So what you're going to summarize from your exercise, this is the one, and this one is your truth table last time for your D and also T. So I hope that you can try your exercise in your module. So now let's move to our design 2-bit synchronized counter. So now you're going to make it much more bigger. This one is under JK flip-flop, the example. So first step to design 2-bit synchronized counter using the JK flip-flop. There is no input or output element in this design. So you need to draw state diagram. And also you need to create your next stage. So for your present state and then your next stage, what we're going to happen. If you can see over here, last time in your previous 1 bits you have 0 to 1 only, because there is two two possibilities only. And now you have a 2-bit, you have to the power of 2, so you have 4 possibilities. That's why you have 0 0 0 1 1 0 and 1 1. So your timing diagram will be your state diagram will be much more bigger. So 0 0 0 1 1 0 and 1 1. So you have your present state 2 bits also. Next state is also 2 bits. Last time you see only Q 0 and Q0n and Q0n plus 1. Now you have the Q1. I hope you understand what is meaning Q1 and Q0. This is on the bit. So this is the examples of your next states. If you can see over here, this one is under 0 0. If let's say you are from your present state is 0 and 0, you're going to move to your next state is 0 1, and then your present state is 0 1, you're going to move to your 1 0, and etc. So this is just an example, because over here it's mentioned there is no input or output element. So as you can see that it is under counter, so it's going to be a count from 0 to 1, 0 1 2 3. That is how you're going to count, right? So that's why it increasing from 0 to 1 to 2 3 and then back again, because it is synchronized counter. So that's why from your present state, if you can see over here, you will move to your next state from 0 to 1, 1 to 0, 1 to 2, 2 to 3, 3 back to your 0 for your initial. And then after that, you need to construct the flip-flop transition table. From here, this is the part that you need to draw the acts, the what happened over there, etc. So over here, let me draw the timing diagram so that you can see it clearly from 0 to 0, 0 1, 1 0, and then 1 1. So from here it moved to here, it moved to here, it moved to here, and then to here. So if you can see, it's moved to here, 0 to 0. What was the condition? If you can see that your previous example in this video and in this slide, so you can see that 0 to 0, you're going to have 0x, 0x. This one is your n, and this one is n plus 1. So similar also over here, you can see this is n, this is n plus 1, but of course this is q0, q0. So from 0 to 1, this is the part. Let me delete first. So from 0 going to be 1. So you can see 0 is going to be 1. This one you need to see at the bit also. So it is 1x. So that's why you have this JK1x. And then for your 1, what happened to your 1 is from 0 to 0. So from 0 to 0, you can see it is 0x. That's why you get this part. Okay, so I give you another example. So from, let's say I give you another one, from 1 to 0. Let's check 1 to 0, it is x1. That's why you have x1 over here. And you have 0 to 1. 0 to 1 is 1x. You will draw like this. And etc. You will follow and refer this through table. So next, after that, after you have all these tables, you need to follow the sequence, right? You will use the step number 5. Use K-map to derive the logic equation. So please take note, it is for present state only if you're going to use your K-map. Okay, so step number 5, please take note, it is for present state only. So you pick this part. And you will put it over here, 0, 1, 0, 1. This is the condition. And you will refer to exactly 0 also. And this one is 0 first. What is going to happen? Let's say over here I derive it. This is 0, 1. This 0, 0. This is for your J0, K0. So 0, 0, you will get J0 is 1. And then 0, 0, K0 is x. Then move 0, 1. 0, 0, 1. Okay, true. So 0, 1, you need to check your J0 is x. And then 0, 1 for your K0 is 1. And 1, 0, going to see over here, 1, 0, your J0 is 1. And similar to K is x. And 1, 1, you see 1, 1 is x for your J, and it's 1 for your K. So until here, please make sure you understand. Stop this video first. Try to make it understand how we're going to translate. And then after that, you will refer to your J1, K1 also similar what will happen like this. And from this part, then you're going to use your K-map methods. X, you still can circle it together. Then after that, you're going to see what is fixed. So what is fixed over here is, this one is 0, this one is moving from 0 to 1. So which one? So you will get is J0 equal to 1. Then after that, you have the K0 over here. You will draw like this also. You will get as a K0 equal to 1. 1x, 1x, 1, 1, x. So what is your J? Where is it? 1x. Which timing diagram I refer? Okay. Okay, wrong. 1x, 1x. Over here, you will get J is 1. J0. And after that, you can see over here, this one is J0. And this one is under your K0. So for your K0, you can see over here, you get K0 is equal to 1. And from here, you need to use your K-map also. This one you will get as J1 equal to 0. Why? Because this one is 0, 1 at Q0, because this one is 1. And this part is K1 is also Q0 because this is 1. If let's say yours like this, let's say I give you example, so you're going to draw like this, so you will get K1 equal to Q0 bar. While if let's say you have like this, let's say this is the X, this one is 0, let's say I give you example, so what you're going to have is K1 equal to Q1. If let's say over here, then it will be Q1 bar. Okay. So what else? Okay, this one is under lastly, which is under your step 6. So what you're going to do is you need to implement it into your counter implementation by drawing the logic symbol. So you have the input of your J and K, it is 1, 1. So first of all, your J, K, J0, K0, it will be 1, which is high. And then you have, of course, this one is the clock. And you have another input J and K. You can see over here, it's connected directly to your Q. So that's why you will get this drawing like this from your K-map implementations. So this is another exercise, you can try it. And now we're going to move to design 3-bit synchronized counter. So basically, as I already mentioned, you have to strong your understanding first for the 1-bit synchronized counter, so you can easily expand it from 1 to 2 bits, and then 3 bits, and then 4 bits, and etc. Still, in this example notes, we use the JK flip-flop. So JK because we have two inputs, J and K. So you have 3 bits for your present state and 3 bits for your next state. For 2 bits you have 2, and then for 1 you have 1, and for 3 you, of course, you're going to have 3. And the counter, it will move from 0 to 1, from 0 to 1 to 2 to 3, 4, until it return back from 7 to 0 back. And what you're going to see over here is the next state, next 0, 0, 0, is going to be 0, 0, 1. And then from 0, 0, 1 is going to be 0, 1, 0, and continue until the rest. This is step number 3. And then step number 4, you need to do the FF transition table. This is the flip-flop transition table. You need to check your JK for each bit. So from here, you need to refer your first transition table for your JK. If let's say 0 to 1, what is your J0, K0 value? If from 0 to 0, what is your JK1 value? And 0 to 0, what is the value? So you need to fill in all. Fill it all. Okay, let me try to fill it. You need to refer this table as I mentioned. 0 to 1. 0 to 1, I have 1x. And then 0 to 0, I have 0x. And then 0 to 0, again, I have 0x. Let's move to another 1 to 0. 1 to 0, I have x1. Please make sure you refer to the bit. So I am referring to the bit. So please make sure you do the same. This one, let's say from 0. This is bit 1. So over here, 0 to 1. So I refer 0 to 1. The JK will be 1x. And you can continue fill it all. That's why you will get your JK transition table like this. And the step number 5, you need to create the K map. So from here, you need to do one by one. First of all, your J0. For your J0, you will have all this, but you need to only refer to your present state. So you have, let's say I give you the example so you can see clearly over here. Say I have 0, 1, and then Q2, 0, 1. This one is 0, 0, 0, 1, 1, 1, 1, 0, like this. Ugly, right? Then you can see over here, let's say it is 0, 0, 0, 0, 0, 0. You're going to see the J0, it will be 1. I'll give you another example. If let's say this one is under your J0, so this part is 0, 0, 1, 0, 0, 1. Over here it is x. Give you another example, 0, 1, 0, 0, 1, 0. It's going to be 1. And then 0, 1, 1. 0, 1, 1. I get x. And you're going to get like this. Basically, it's similar, only the different on the dimension. But similar, I did a vice versa. Where is my J0? I did like this, right? Q0, Q1, and then Q2. But basically it's similar because you refer to the similar truth table. and please make sure you refer to the present state, and also your JK transition table. From here, if you draw like this all together, what you're going to get, if let's say all is going to be true, you're going to get 1. And similar to here, K also. And then over here, if you look into what will remain the same, it is this part, which is under your Q0. Similar also here, and etc. I don't want to show and repeat again about the K-map, because K-map I already touched in deeper last time. Hope that you also can understand it. And lastly, under your step 6, to implement the 3-bit synchronized counter. How it's going to look like? You have 3 blocks of your JK flip-flop. So this one is JK0, and then JK1, JK2, K1, K0, K1, K2, similar. So what you going to do, I think over here, this is my J0, K0. It is 1. So I will connect it together to high. Of course, you're going to have your clock, isn't it? And then you have the output Q. This one is, of course, you use 0. And after that, this is my input for board. For board. So this is for board. J1, K1. You have the clock, of course. And after that, you can see over here, this one is Q1. JK. This is the JK. JK is dot Q0 dot Q1. You can see over here. So this is your Q1. Q1, let me put like this. Q1. Okay. I don't know the answer. I didn't try yet, but I think it's going to be like this. This is my K2, and then K2. So is it my my counter is correct? Yes, it's correct. So this is how you're going to draw your 3-bit synchronized counter, and this is the display timing diagram, what will going to be. I think this part also is quite easy, just for you to get the output, and also the output for your each Q0, Q1, Q2, and etc. Depend on what type of flip-flop, of course. Please read the notes. And this is the exercise, but it is using the T flip-flop, and please try to do also. And lastly, on your 4-bit synchronized counter, I think it's already easy, because you already look into 1-bit, 2-bit, and 3-bit. And there is also another example on exercise on design 3-bit synchronized counter for JK flip-flop based on the timing diagram given. But you can see over here it's slightly different with your counter, which is, it is from 0 to 1, to 3 to 2, and then after that this one 4, 6, this one is 7, and then this is 1 0 1 4 5. So it's 4. So please try to do it. If let's say you understand how it's going to move from current present state to next state, so you can easily draw the timing diagram. Only that you need to follow the step slowly, but after you master it, of course you can draw it easily. And there is also all this one is under exercise. Please try to do it on your module also. And next is under 2-bit down synchronized counter. This one is under the flip-flop. So the difference which is down synchronized counter, there is no input and output. Okay, this is the hint. So you need to know how you're going to move, which is from up to down. Is it the correct term? But it is not a counter which is from below to up. This one is from up to down. So from 0 to 0, which is basically I'm going to start with 1 1. From 1 1 is going to go to 1 0, and then from 0 to 1, and then go back to 0 0. If me, I'm going to do like this, but it's similar. It's just a similar, only on our understanding. Of course, it is down synchronized counter, so it will be from up to down. From this one is 3 to 2 to 1 to 0, and continues. And it's just a similar things, only that it is on the vice versa way. But if you can see over here, this is the two tables, present state and next state. This is the next state table. You can see over here, if let's say you are moving from 1 1, you have the present state of 1 1, you're going to move to 1 0. So you need to refer to this part first. If I am like this, so it will be moved to 1 0, and after that from 1 0 it's going to move to 0 1. This one, right? And then from 0 1 it's going to move 0 0, sorry, to 0 0. And from a 0 0 you're going to continue to 1 1, and just similar to all, but this one you need to refer to the D flip-flop, not your JK anymore. So please try to do it. And this one is 2-bit up or down counter. So over here you can see that you have the O. So that's why you have either it's going to let's say you have 0 1. I draw it in decimal. So basically you need to know it is 1 1 0 0 0 1 1 0. But what I want to show is from 0 it can go to 1, it can also go to 3. Similar also over here, from 1 it can go to 0, it can go to 2. From 2 it can go to 1, it can go to 3 because it's up and down. Sorry. And from 3 it can go to 2 to the down, and it can go to the up. So that's why you will get the state diagram like this. And there is another one notes that you need to know, whether counter up. Under counter up, we're going to get x equal to 0, and counter down, x equal to 1. So this is the condition given. But basically, if you know the first step, you will notice that it's easy. Later on, it's just a similar. So this one is the input of your x. When it is 0, what happened, and etc. Similar, you can see if 0 0 and your x is 0, you're going to move to 0 1. So you can see over here, and follow all together. This one is counter up because this is x, x equals 0, counter down, x equals 1. And follow the step until your step number 6. Until your step number 6. After that, you get this one. Try to draw the diagram. This one, the example, under your exercise, you can refer to your module. And next is under our counter for arbitrary sequences. So this is the design the counter based on the given state diagram. So this is the state diagram given. This is under T flip-flop. The counter is 3-bit counter because you need to see because you were given only the diagram. So what you can come out, it is 3-bit counter. The total state is to the power of 3, of course, if it is 3-bit. You can see 1, 2, 3 bits. And it only have 4 states. 1, 2, 4, and 5 and 7. You need to come up with the value. This one is 2, 5, and 7 in the decimal. And other state is invalid. So invalid, it never occur or don't care situation. So get it right? So next, you're going to draw it in your state table. Under state table, you need to see the next state. So if let's say you have, first of all, you have 0 0 1. So this is my 0 0 1, 0 0 1. The rest is 0 0 0. It is don't care, right? And let me draw the don't care first. 1 2 3 is don't care. Where is 3? 4 to 5. 3 and then 4. Okay, over here we have 5 to 6. Where is 5? I think I draw. Okay. After that, if let's say over here you can see 0 0 1. This is going to move to 0 1 0. 0 1 0. 0 1 0. You will directly go to 1 0 1. After that, you can see over here 1 0 0. It's don't care. Next, you until 1 0 1, you will move to 1 1 1. And then over here, it's all don't care, isn't it? And from here, 1 1 1 is going to go to your 0 0 1. This is how your next step will happen. I show you this part only first. Then after that, you're going to refer to, what about my battery? Sorry, I need to check my battery first. 4%. Okay, I can continue first. Okay, I try to finish it first, then I will need to charge and stop the video. Okay, next is, and you can see over here, where is my microphone? It's going too far from me. So over here you can see that your T flip-flop, this is your T flip-flop. For T1, you can see over here, if let's say your Q your present state, and then this is your next state. If let's say your next state is equal to your present state, so your T will be 0. If let's say your next state, okay, I give you an example first. Okay, we refer to Q0, T0. You can see over here, this is your present state. Your present state is 1, and then your next state is 0. So if let's say your next state over here is Q, you can see over here, this one is QN, or QN over here is 1. So your QN is 1, and your present state is over here is 0. If let's say it's going to be happen like this, but your QN is 1 over here, and your QN plus 1, which is your present, is 0. It is the bar, or it can say is not, or complement, or toggle. So that's why you will refer this part. You will get 1. And then another example, this one is also toggle. I'm not going to see it because this is the part. But when your present and also your next state is similar, which part? Okay, this one. Your present and next state is similar, so your output will be 0 for your T. It's not your output, it is T value of your flip-flop. Going to get 0, similar to this part. Okay, I want to check another one, and let's say over here, there is no 0, 0. Okay, this one. This is the Q2 for next state and also present state. Similar, both is 0 to 0. So that's why you're going to refer to this one. So you will get 0. Get this step. Okay. Then follow by all the step that we already learned in previously. So that's why we already covered this part. I think it's just easy, okay, can be understand, but you need to have more exercise. Please try to do a lot of exercise so that you can get familiar with it. So this one, another example exercise, you can try to do it. So under synchronize BCD decade counter, I'm going to show it on our next video. So I need to end up first until here. So stay tuned to another video. Okay, bye bye. I cannot.